Okay, hello. On this video, what I'm going to do is I'm going to talk a little bit about the section involving weak bases. We've already discussed strong acids and strong bases and weak acids. Now we're going to look at weak bases, which follow a similar procedure for dealing with as the weak acids. So let's take a look here. I'm going to go ahead and bring up so this is section 16.6. I'm going to bring up the most common types of weak bases. So the most common are the nitrogen bases. So ammonia is a good example of this. Ammonia is an interesting molecule in that if you dissolve it into water, it will react with the water. And the water will donate a proton, a hydrogen ion, to the ammonia. It's a reversible reaction, and what you'll end up with is ammonium, NH4+, and then the water minus CH+, is the hydroxide ion, OH-. This is called ammonium. When the name of a compound ends in IUM, that typically means it's a cation. It's positively charged, like aluminum, beryllium, for example. And this is ammonia. So if you think about it, if the proton is moving from the water to the ammonia, then what's happening is this is accepting the H+, which would make it a base, right? That's our Bronsted-Lowry base. The water is donating or transferring the H+, so we would call it an acid. This over here would be the conjugate acid. Remember, the product side are conjugates, so that's the conjugate acid, and this is the conjugate base. Okay, so it's typically about the same with other nitrogen type compounds. So for example, CH3NH2, which is called methylamine. Same idea, it dissolves into water. The water transfers a proton to the nitrogen. It actually attaches to the nitrogen. And you get CH3NH3+, and then you've got the hydroxide ion. So notice with this type of base, you get the hydroxide at the end, right? And that's what a base does. It generally produces a hydroxide ion, right? So this is behaving like a base, but notice I'm using the equilibrium arrows here. It's a double arrow, right? So that means it's a weak base. Well, actually, I should write that this is the weak base. Okay, so we'll talk about the equilibrium aspects of that as well. What I want to do is I want to show you the first type of problem here. Oops. Here we go. So the first type of problem is just to be able to recognize some of these acids and some of these bases here. So here's the first one. So some soluble compounds are listed in the table below. Complete the table by filling the name or chemical formula for each compound, whichever is missing. If there's more than one way to name a compound, choose the name when the compound is dissolved in water. Also classify the compound using checkboxes, okay? So the first one is ammonia. Well, we did that one, right? That's NH3. Just went over that, NH3. No metals in it, right? It's a molecular type compound. Non-metal nitrogen, non-metal hydrogen. So that's molecular. And it's a base, right? It's a weak base. We just showed how it produces the hydroxide ion. Acetic acid, well, we know that's an acid, but what's the formula? Well, you can look it up, but it's HC2H3O2. It is, again, acids are generally molecular compounds, and it's a weak acid. Perchloric acid, well, that's HClO4. That is, again, it's an acid, so it's a molecular compound, but it happens to be one of the strong acids. Sodium perchlorate, now that's an interesting one. Sodium perchlorate, NaClO4, is not an acid or a base. It doesn't have, doesn't produce any hydroxide. There's no nitrogen to react with water. Doesn't have the hydrogen to give off. So it's not an acid or a base. In fact, it's a metal with a nonmetal, and metals with nonmetals are ionic compounds. Okay, so that's our first kind of look at that, is just how to classify things. For the most part, with the weak bases, we're looking at these types of compounds like ammonia, methylamine, any other compound that has that nitrogen in it. Okay. So let's see if we can bring up another one. The next skill that we want to look at is writing the chemical equations for these weak bases. I just did it a moment ago, but also writing the expression, the equilibrium expression. So here's an example, writing a base protonation constant expression. Fill in the left side of the equilibrium constant equation for the reaction of diethyl methylamine, a weak base with water. Cool compound, diethyl methylamine. But the point here is, see how you have that nitrogen there? The nitrogen is going to be bonded to a couple of carbons. I'll actually write out to go ahead and give you the structure, but you don't need to know the structure, just the formula to do this. Okay, so let's take a look at this one. So it's diethyl methylamine. Okay, I'm going to show it to you. Okay, amine typically means nitrogen, or it means nitrogen with some number of hydrogens, typically, anyways. So methylamine. So what we have here is methyl is CH3, and then it says diethyl. So there's two of these C2H5s. That's an ethyl group. Okay, C2H5, C2H5. And then you got one methyl. So the condensed form of that would be, you have 5 carbons, so C5. You have 10, was it 13 hydrogens, and then 1 nitrogen. Okay, we'll assume that it dissolves in water. It is a weak base. So we're going to react it with H2O. Water will donate the H+. It's a weak base. So I'm going to write it this way, NH+, right? Just, you know, the proton is going on to the nitrogen. You could write C5H14N+, and that would be okay too, but I'm going to write it with that extra hydrogen. Okay, now the question is, how do we write the expression for equilibrium? Just like the weak acids, we do the products over the reactants. So the first product is right here. Second product is right here. And then you have a reactant over here. It's as simple as that. Of course, water is not included because it's a liquid. And there you go. So there's the equilibrium expression for this particular weak base. It does have a KB value that we could look up. Let's see if we can find another one. Okay, let's take a look at this one. Again, writing the base protonation constant expression. Fill in the left side of the equilibrium constant equation for the reaction of 4-bromoaniline, C6H4BrNH2, a weak base with water. Again, it's telling you it's with water. Okay, so this is called 4-bromoaniline. I want to show you that structure as well, just to kind of give you an idea of what these structures look like. So aniline is a modified benzene ring. It has the benzene ring, but it has an NH2 group attached to it. That's aniline. And then the number is 1, 2, 3, 4. It has a bromo here. Okay, so that's 4 bromo aniline. And again, what happens is the water is going to react with the 4 bromo aniline. The proton is going to go into the nitrogen. And then you're going to be left with, well, you have this benzene ring. It's called an aromatic group. Now you have 3 hydrogens and a plus charge, right? And then you have this bromo here, and then the water loses the H plus, so you've got hydroxide. Okay, presumably these are all soluble in water. Now, if we want to use it in terms of the formula, it would be C6H6 Br. Let me make sure I got that right. 1, 2, 3, 4, 5, 6 plus H2O. Oh, I'm sorry, forgot the nitrogen. Let's do it this way. C6H4 NH2Br. See how I'm writing that? C6H4 NH2Br. So C6, the 6 carbon ring with the 4 hydrogens. Remember, there's a hydrogen coming off each of these carbon atoms. So that's where the H4 is coming from. Okay. And that's going to react with the water. Again, the hydrogen is going to go on to the nitrogen. So you get C6H4 and NH3Br. And then again, it's a little tricky how you write the plus. It's so tricky because we might, from that, infer that the bromine is the one that actually has the positive charge. So we guess we could write it this way. That would be another way to do it. Okay. There's no one way to do it. The point is now we want to write the equilibrium expression, Kb. So that would be the concentrations of the products. So here's our first one. I'll use this one here. Here's our second one here. And then we have one reactant there. So C6H4 NH3Br plus times OH minus over C6H4 BRNH NH2, or I'm sorry, NH2Br is the way I was writing it. Okay, again, water's left out because it's a liquid. We leave that out. Okay, so products over reactants. So just like Ka, the higher or the greater the value of Kb, the stronger the base. Okay, so if I gave you several values, okay, see all those values of Kb? So I put in a particular order. It's increasing in this direction. Okay. What that means is as it increases, it's getting stronger. Remember, a base is something that forms hydroxide. You can think of it as that way. So the more hydroxide a base forms, the stronger the base is. The larger the value of K, the more you're going to have in terms of products. So if you have more products, you have more hydroxide. So it would be considered a stronger base. Not a strong base per se, but a stronger base. And these values can get pretty small. You could have values that are all the way down to say like 3 times 10 to the minus 13. It's pretty small. You could have values that are even larger than 6.2 times 10 to the minus 5. But the point is, the stronger the base, the greater the value of KB is going to be. Okay. Strong bases really don't have KB values because they're so strong they dissolve 100%. There's nothing in the denominator left, right? So for example, if I say, hey, NaOH is going to form Na plus and OH minus, and I try to do a KB for that. I mean, in theory, you could write it out. You could write out the expression. But the problem is, since it's fully soluble, this is going to be pretty close to 0. So what do you get for KB if the denominator is 0? Essentially, it's undefined. You don't really have a value. It's huge anyways, right? So typically, the strong bases don't have KB values. We just say, hey, they're just strong bases, so they produce a lot of hydroxide. The weak bases are the ones that are given values. They're measured values and all of that. And those are, typically 10 to the minus 5 or 10 to the minus 6. Okay. So let's take a look at a calculation then. So that was just writing the expression for KB. And again, notice how it's a lot like doing the expressions for Ka. We're now going to calculate the pH of a weak base solution. So let me put this one up. This is for ammonia. Again, ammonia is like just the exemplar of a weak base. It's the one we use. It's a simple formula. It's just well characterized. We use ammonia as the examples over and over. If you go online or if you look at any textbooks, you're going to find KB calculations with ammonia are plentiful, right? So calculating the pH of a weak base solution, the base protonation constant KB of ammonia NH3 is 1.8 times 10 to the negative 5. Calculate the pH of a 0.42 molar solution of ammonia at 25 degrees C and round your answer to 1 decimal place. Again, KB values, just like Ka values or Kw, equilibrium constants in general, are defined for particular temperatures, or at least they're characterized for specific temperatures. So if we were doing this at 75 degrees C, ammonia would have a different KB. So that is often why you'll see 25, just so that we know that. So they give us the value there. It's 1.8 times 10 to the negative 5. And again, that's a typical type of problem. So here's what we're told. We're told that the initial concentration of ammonia, so I'm going to write I again for initial, is 0.42 molar. It's going to react with the water to form, again, it's a weak base, right? So you have to recognize, oh, you got this nitrogen, it's a weak base. Protonates, the water protonates it. By the way, water can protonate bases, but it gets protonated by acids. Okay, it's amphiprotic. It can act as an acid or a base depending on what it's reacting with. Okay, so you get the ammonium ion at H4 plus, and you get the hydroxide ion, OH minus, right? We all know the hydroxide ion now. So what are we told? We're told the value of KB. We're told the initial value. Liquids we're not going to worry about because liquids are, not included in the equilibrium expression. These concentrations are initially 0. So even without knowing the value of KB, we know this will be minus X and these will be plus X. Why? Well, think about it. If you're going to have any value of K, you have to have some amount of products. Nothing can be 0. You can't have 0 concentration of hydroxide and have a KB value. It will give you 0. You can't have 0 for ammonium. That would give you 0. So it's impossible to be at equilibrium and have any of these species be 0. So if something is 0 and it can't be 0, it's got to increase. So they have to go up by X. But the only way they can be increased is from the ammonia. So the ammonia's got to go down. So it's minus X. And then at equilibrium, you just take the initial and the change. Initial and change, initial and change. And there you go. There's your equilibrium expressions. Now it's time to write out the expression for KB. It is the concentration of ammonium times the concentration of hydroxide over the concentration of ammonia. And we already know it's 1.8 times 10 to the negative 5. Okay. So now we can substitute these in. These ones right here. So that's equal to x times x over 0.42 minus x equals 1.8 times 10 to the minus 5. But remember what I said for weak acids. If the value of K is much less than the initial concentration, now think about it. The initial concentration is 0.42. The value of K is 1.8 times 10 to the minus 5. So that's thousands of times smaller. If that's the case, then X is going to be very small relative to the initial concentration. X is going to be much less than 0.42. And another way of kind of thinking about that would be like if you have a lot of money and you lose a nickel, it's not a big deal. So if you start off with $1,000 and you lose 5 cents, it's not a big deal, right? Now, if you have $1,000 and you lose $500, 50%, that's a significant change. But a nickel out of $1,000 is small. So this value here is so small, we can just ignore it. So we'll just say that 0.42 minus x is approximately 0.42. Now you do have to be careful. If this was like, 0.1, then 0.42 and 0.1, not that big of a difference anymore. So then we wouldn't be able to make that assumption. At least there would be some error associated with that. But when you have a value of K that's 1,000 times less than the initial concentration, perfectly good assumption. So that simplifies it. X times x is x squared. 0.42 minus x, we're just going to write that as 0.42. And that's going to be 1.8 times 10 to the negative 5. We're going to solve for x because the x is going to give us the concentration of hydroxide at equilibrium. So that's why we're going to solve for x. That's why we go through the algebra of these problems. Okay. So let's rearrange it. I'm going to multiply both sides by 0.42. Okay, x is going to be the square root of that, right? You just take the square root of both sides. Okay. Oops, sorry about that. A little bit of a problem here. A little bit of a technical problem here. But we'll resolve it in just a second. Here we go. Okay, so let's move this to scientific. There we go. Okay, so 0.42 times 0.000. I'm using an awkward scientific calculator here. It's taking me a while to do it, but we're going to get a number here. Okay, so it looks like it's 2.75 times 10 to the minus 3. Okay, so there's our x. Again, the x is the hydroxide concentration. Okay, so now we can't calculate the pH directly because this is not the hydronium concentration, it's the hydroxide concentration. So let's figure out what POH is. Remember, POH minus the log of hydroxide concentration. So that would be minus the log of 2.7 times 10 to the minus 3. So it's 2.56. So just be careful. You got one more step to go, and that is the pH is 14 minus the POH. So that's 14 minus 2.56. Okay, so that's like 11.44. And there you go. That's pretty basic, right? Ammonia is a base. So if you're calculating the pH of the basic solution, it should be basic, right? Or pH of the base in water. That solution should be basic, and in fact it is, okay? So for this section, there's not too complicated a problem. It's the standard problem of giving you the initial concentration of the base, giving you the value of K, writing out the equation, writing out the ice table, substituting back in and solving for X. X is the hydroxide concentration, so we calculate the POH. And then we take 14 minus that to get the pH. And that's generally what we try to calculate here is the pH, okay? So, you know, relatively simple problem if you've gone through the weak acid problems. There's not, you know, not much else going on with that one, but it will be important when we get to the next next chapter in any case, okay? So in the next video, we'll start looking at the relationship between Ka and Kb for weak acids and weak bases. That'll be important when we talk about buffers. And so take care.